In the last video, we showed the process that we will use to solve physics puzzles. The same process will apply in all cases, but sometimes applying it can be a bit more challenging than in the comparatively straightforward examples we showed in the earlier video. Here is a person jumping on a trampoline. As long as this person is in the air, they are in free fall, but the instant they come into contact with the trampoline, free fall doesn't apply anymore because the fabric will slow them down. Your textbook might ask a question like this. Someone jumps on a trampoline. He touches the surface of the trampoline at a speed of 3 meters per second. The trampoline deflects by 0.6 meters before propelling him upward again. What is his deceleration in meters per second square, and what is his deceleration in terms of g? Before we begin, you might notice that word deceleration. I personally dislike that word. I think it's ambiguous and redundant. Instead, I mentally replace the word deceleration with acceleration. So the question becomes, what is his acceleration in meters per second squared, and what is his acceleration in terms of g? We can solve this puzzle using our process. Here is the drawing. He makes contact with the trampoline in the left picture, and the trampoline fully deflects in the right picture. We consider the time of contact to be when we took the first photo, and the full deflection the second photo. We can set the origin at the level of the trampoline and upwards to be the positive direction. The unknown in the question is the acceleration. What is known? He was traveling at 3 meters per second when he made contact with the trampoline, as we see in the first photo. That's 3 meters per second downward, or, given the way our axes are set up, -3 j hat meters per second. He travels 0.6 meters downward as the fabric deflects, so the displacement is -0.6 j hat meters. At the point of maximum displacement, the trampoline has brought him to a complete stop, so his velocity in the second photo is 0. So we're solving for acceleration, and we have displacement and initial velocity and final velocity. The only one of the toolbox equations that contains these 4 quantities is number 4. So we use that and we solve. His acceleration works out to 7.5 j meters per second squared. The other part of the question asks for his acceleration in terms of g. This is just asking us to say how large his acceleration is relative to acceleration due to gravity, which is 9.81 meters per second squared. We divide, and we find his acceleration is 0.765 g. A subtlety can arise when the object we're tracking starts from a moving source. Here's a hot air balloon rising into the wild blue yonder. Consider this situation. A hot air balloon rises at 5 meters per second. When the balloon reaches a height of 30 meters, a child in the basket drops a ball overboard. How long does it take the ball to land? We can draw a picture and set the endpoints of the motion. Photo 1 corresponds to a nanosecond after the ball was dropped, and photo 2 corresponds to a nanosecond before it lands on the ground. We will set the origin at the ball's position in photo 1 and downwards to be the positive direction. The question asks us how long it will take for the ball to land. That means time is the unknown. But before we set our knowns, we have to watch out for one fact. The hot air balloon is rising, and since the ball is moving with it, the ball initially has the same velocity as the balloon. The ball has to move up, reach its peak, and then move down. Since we set downwards as positive, the ball's initial velocity is the same as that of the balloon, which is -5 j hat meters per second. Overall, the ball will land 30 meters below its starting point, so its displacement is positive 30 j hat meters, and it is in free fall the whole time, so its acceleration is positive 9.81 meters per second squared. The only equation to weave together time, displacement, and initial velocity and acceleration is number 2. So we use it, and we get a quadratic equation. We can solve that with the quadratic formula that we saw in lesson 2. We get 2 possible values of time, of which only the positive one can be correct. It is 3.03 seconds. It takes 3.03 seconds for the ball to land. Functionally, there is no difference between this puzzle and the one from the last video where a rock was thrown upwards off a cliff. It's just that the initial velocity of the object in this case arises from a different source. In some puzzles, an object isn't moving at constant acceleration. In order to use the toolbox equations, we need to break up the motion into discrete chunks where acceleration is indeed constant. Consider this example. An athlete runs a 100-meter dash. She starts from rest and accelerates at 2.5 meters per second squared until she reaches 6 meters per second. She then remains at this speed. How long does it take her to finish the race? This seemingly innocent question actually has 2 accelerations in it. In the first part of the puzzle, the athlete accelerates at 2.5 meters per second squared. But after she reaches 6 meters per second, her velocity remains constant, which means her acceleration is 0. We solve this puzzle by breaking it into 2 parts, and one way to do that is by taking 3 photos. The first is at the instant our protagonist starts the race. The second at the instant she hits her stride and stops accelerating. And the third when she crosses the finish line. We will set the origin where she starts running and her direction of motion as positive. We will call the motion between photos 1 and 2 phase A, and the motion between photos 2 and 3 phase B. We'll analyze them separately because these 2 phases of motion have different accelerations. Let's examine phase A. The unknown is t sub A. The runner starts from rest, 0 meters a second, and has an acceleration of 2.5 meters per second squared. And the velocity when photo 2 was taken is 6 meters per second. That's the final velocity for phase A. So we know initial velocity, final velocity, and acceleration, and we're looking for time. The only toolbox equation that weaves together all 4 of these quantities is number 1. So we use this and easily solve for the time in phase A. It is 2.4 seconds. Now, phase B. The unknown is time sub B. We already know the velocity of the runner at photo 2 is 6 meters per second. And if she remains at this velocity, then her final velocity at photo 3 must also be 6 meters per second. But at this point, we're stuck. We need 3 pieces of information to use any of the toolbox equations, and we don't have that. What do we do? There's one piece of information from the puzzle that we haven't used yet. This was a 100-meter dash, which means the total displacement of the protagonist across phase A and phase B combined was 100 I hat meters. If we knew the displacement of the runner in phase A, then her displacement in phase B must be 100 minus that. Let's return to phase A. We have so much information that we can easily solve for the displacement. Let's use equation 4. Plugging in the knowns, we get a displacement of 7.2 meters. That means that in phase A, the runner displaced by 7.2 meters, and in phase B, the displacement must be 100 minus 7.2, which is 92.8 I hat meters. Now we return to phase B. We finally have 3 pieces of information for this phase: displacement, initial velocity, and final velocity, and we can solve for the time. The only equation that weaves together these 4 quantities is toolbox equation number 3. We'll apply this and solve for the time. It is 15.47 seconds. To conclude, we found that the time required for phase A, the acceleration, was 2.4 seconds, and the time required for phase B, the constant velocity section, was 15.47 seconds, for a total time of 17.87 seconds. Our protagonist took 17.87 seconds to complete the 100-meter dash. Sometimes you will have to use multiple photos even when the acceleration is constant. This can occur if you don't get sufficient information about the motion of an object between just two photos. Here, a child drops a ball from the top of a building. You are inside the building and you see the ball fall past your window. The window is 2 meters tall and the ball fell 7 meters before it reached the top of the window. How long did it take for the ball to pass by the window? Start by drawing a picture. You probably guessed that we'll need to take photo 1 as the ball crosses the top of the window and photo 2 when it crosses the bottom. The question asks, how long did it take for the ball to pass by the window? So it's asking for a time. The knowns are the height of the window, which must be the displacement of the ball, and the acceleration due to gravity. But after then, we're once again stuck. We don't have 3 pieces of information between these two photos. We need another piece of information, like the initial velocity at photo 1. Here's how we solve this. We're going to take another photo, photo 0. Photo 0 will be taken a nanosecond after the child dropped the ball. We'll analyze the motion of the ball between photo 0 and photo 1 when the ball reaches the top of the window. We'll call this part of the motion phase A. In phase A, we have the displacement of the ball, 7 meters, the initial velocity, 0, and the acceleration, 9.81, and we're looking for final velocity. The only toolbox equation that uses these 4 variables is number 4. Using this, we can easily solve for the final velocity as being 11.72 meters per second. Now, the final velocity in phase A is very handy because it is also the initial velocity of the ball in phase B. With this initial velocity, we now have 3 pieces of information and we can use equation 2 to solve for the time that it takes for the ball to fall past the window. It works out to 0.16 seconds. In this video, we looked into more challenging kinematics puzzles. In the next video, we will apply the rules of kinematics in 2 dimensions.